perfect. So I guess I don't speak Dutch, right? Yeah. Okay. Perfect. So yeah. So thanks first of all for having me here, and best of wishes for this year. So indeed, I would like to talk mostly about the approach that we are working on, which it's quite a mouthful maybe and hard to remember, but quantum-centric data-driven R&D. So basically, it's an idea that we developed based on our existing people that are working on data-driven R&D. Basically, everything on quantum chemistry approaches without any quantum computers, but kind of swapping in quantum computer as a sort of a core element. But just as an outline a bit, I would just like to say a few words about why we are interested in this from CapGemini and what we do specifically on the quantum side, and then move a bit deeper into the methods, into the chemistry, and some of our results on hardware and the follow-ups. So let me very, very quickly, maybe the less sciencey parts to start with is that so my role within CapGemini is to lead the quantum team. So we have a lab, the Quantum Lab, which is a worldwide network of people. My role is to coordinate that. I did study physics here at the university, Advanced Matter and Energy Physics, some time ago. But then since then, I've moved into this role of coordinating this team. So there are people that in my team that are really deep in the chemistry or the physics. I have a bit of an overarching thing and might not know all the details that some of my guys do. But overall, it's all like a quite deep technical team that is there to research new applications, and it's really pre-commercial. So I really like that because the rest of CapGemini is much more of a consultancy technology firm, and we just get to play around with technology and do research. And so we do a bunch of things. So I'm going to focus a bit more later on the specific thing, quantum-centric data-driven R&D, but that's not all that we do. Ultimately, I guess the point why we have a quantum lab is because in the end we want to reach our clients, right? So that's big pharmaceuticals, that's automotive companies, that's every big Fortune 500 company basically. And so the goal in the end is getting them ready to actually use it and trying to bridge the gap both from a technology as from a sort of business readiness perspective to help them make use of that. And across everything that we do, the key value proposition or the key focus is trying to do that as a system integrator, right? So we're not a product company that IPs or licenses one product. Instead, we try to work with whoever has something interesting, either academia or startups or other vendors, and try to apply that in actual cases. And then also trying to scale that up, right? So my team mostly consists of quantum physicists and quick chemists and related, but we work with a larger team of business people or also researchers, but then in specific fields like in battery science or something else. And so there's a bunch of focus areas that we have. So the first one really is on consultancy, and sometimes it's, as you may know, there's a lot of companies out there that know really nothing about quantum, and there's a long way to go to get them to understand something. So a big part is just trainings to awareness, but eventually also maybe more road mapping. We do some work, for example, for the European Commission on policy and these type of reports. So there's a quantum-centric data-driven R&D. I will dive into that later. Post-quantum cryptography, of course, is a big topic, and I guess that's interesting for us because it's massive, right? There will be a massive migration, and a lot of the work will be pretty cumbersome, maybe, right? Like all kinds of updates and legacy migration. We do some work with Pascal, so the neutral atom analog simulators, and then mostly on optimization challenges. So really using most of our sort of classical optimization techniques and all the heuristics that are there, but then applying those to neutral atom technology. And then a bit more lower down the stack, really on sort of core algorithms. So for example, we have a team that really developed a new version of amplitude estimation with different sampling routines, mostly with the aim to use specific insights that you may have of an application to create a better or shorter circuits. And finally, more on the hardware. So, for example, we have a quantum sensing team that really did much of the signal analysis of magnetometers and trying to optimize them for a case. But I guess maybe the most interesting and the most the one that we're talking about today is about quantum chemistry. So quantum-centric data-driven R&D. And so I guess, I mean, it's probably not new for anyone, but it's very exciting field, of course, right? It's one of the fields where we generally think that there is potential for quantum computer because there is such a fundamental quantum nature in many systems. And I think sometimes it's maybe underestimated. People look for all these different applications in finance and optimization and elsewhere, and but even if this would work, that's already groundbreaking for so many industries. So many of our automotives are interested, and many of our pharmaceutical clients, and wherever, energy utilities, etc. So that's really enough already. And so also many of these things, we know that there is not just ultimately some quantum behavior, but pretty emerging macroscopic quantum behavior that can be quite descriptive for these systems. Systems, for example, that have transition metals are very difficult to explain classically. We know that many of these systems have a lot of issues with their current systems if they use DFT because it's not accurate enough or because it takes too long. We know in therapeutics that even in phase 3 trials or later down trials, there are still things that you find that you could have found earlier if you had better simulations, right? So it's not just that they are intrinsically quantum mechanical, but also that we know from practice that our current methods are not good enough, and therefore perhaps quantum computers maybe. At the same time, I guess, so this is also the sort of the motivation of how we came to this framework, is that there is a lot of progress, of course, in machine learning for these type of systems, and it's not to be underestimated how much that can deliver. I think honestly, for example, systems like maybe protein folding, there's some cases where a quantum computer might still do something new, but in the vast majority of at least the cases that I think we've worked on, it's pretty much solved, right? And of course, there's some edge cases, and that might be not everyone might agree, but I think in many cases at least it is very powerful. And so what we want to do in any way is to see how can we acknowledge that AI is very powerful, and how can we not try to beat it really, but really work alongside of these AI tools. So then the question is like, how do we get from sort of the quantum algorithms that we have today to really what our clients are interested in? And I think that that sometimes is a bit overlooked, right? Like in the end, clients are interested in how can we, cut off a couple of years down a drug development cycle from 10 years to 7 years, or how can we, increase the capacity of a battery by 10%? And these type of questions, and it's of course not what is getting out of a quantum computer. If you go one level deeper, maybe indeed what companies are interested in is maybe what is the reactivity of some drug, or what is the toxicity, or what is some degradation pathways that we want to understand better. And these things aren't really coming out of a quantum computer either, right? Many of these properties are defined by bulk systems, and maybe not very explicitly defined, and they're definitely not just ground state energy. So there's all kinds of challenges where that we want to address that we can't just address with a quantum computer. At least definitely not a ground state solver or something like that. And so the question is, how do we go from what we can do with a quantum computer to making it useful? And I guess these are just some of the points, of course, that everyone is working on, including us. And really then thinking about how can we integrate this with AI, with the data sets that we have available. How can we treat the treatment of noise, not just by the hardware or sort of the low-level quantum algorithms, but by the whole end-to-end workflow. And how can we make it, well, how can we make it useful, I guess. So this was sort of the motivation where we started. I wanted to, and this is my colleague Sam that is driving a lot of the work, take the approach that we developed in the case of one particular case that we worked on with GSK, and then later I'll give a few other works that we worked on as well. And this work was on the prediction of reactivity for covalent drugs using computed quantum features. Right, so this is the combination already of AI and quantum computers by using a quantum computer to compute certain features of these systems and use them to predict reactivity. And I think so. One point here to mention is that, of course, this approach you don't necessarily need a quantum computer for. You can compute your features, your quantum features, in any way that you want. But we pick those features in such a way that we hope that there is a potential for a quantum computer. Right? Because they are very quantum mechanical in nature, they're probably difficult to solve classically and therefore might work better on a quantum computer. And so the framework, and I got through it one by one in a second, is basically composed of these sort of fundamental steps. But the first part is we want to really work on cases where there is potential for quantum computers, right? So if there is something that, and that's really not a trivial question, I guess, because you want to treat systems that are showing interest in chemistry, that they're too difficult for classical computers, but not too big for quantum computers that they're 100 years away. You probably want to think about systems where you might have small subsystems that are interesting that you can calculate on a quantum computer, but then you want to look at bigger systems, so you want to have a way how you can think about how you can embed different solvers at different length scales. You might want to think about if there is data available for these systems, so that you can also use downstream modeling. And if you check those criteria, it's not so easy. Not every system is applicable. So that's already a big part of the work. Then if you would go, so that's the first part, really finding out what are the systems that are chemically interesting, are feasible enough for the relatively next 10 years or so, have data and have experimental truth data to compare with, that we can start to model. And then the next thing we do is really think about how can we fragment that out? How can we find the small parts that are addressable for a quantum solver that deserves a full quantum mechanical description? And how can we have a larger part that is maybe treatable with some other quantum mechanical solver, but not in full accuracy? And how can we maybe have an environment as well? Moving to active space and that you can select, that's of course a lot of that work is sort of classical quantum mechanical, but you really want to adapt that to the quantum resources that you have. Then evolving your system so that if we have this small fragment that we want to use a quantum simulator for, what are the features that we can extract from that system that will be descriptive for later tasks, right? So that could be, suppose that we have and I'll go to some of these examples later. You have a medicine and there's the reactive side, the warhead, it's called. How does that? Is there some electron transfer? How can we simulate maybe some time evolution of that system? And how can we use that feature for tasks? And then later going to machine learning tasks for that. And so there's all kinds of things that you can think about, right? So in the first phase for the embedding, there's different ways of fragmentation strategies, different ways of minimizing the extra space that we want to use. There's all kinds of different smart ways, of course, for embeddings. We mostly worked with density matrix embedding theory, but there's a whole bunch. We did quite a lot of work on different sort of trying to find the right observables that we measure in the right simulation, electrodynamics to simulate. And that is not something that, so it's one thing you can do that with just your chemical intuition, but it's potentially also quite interesting to make that process data-driven itself. Right? So trying to select features that are maybe less resilient, more resilient to noise, or more descriptive, and sometimes that's not always easy to just do it by chemical intuition, or of course really choose hardware efficient features. And then finally, in modeling, I guess if you have very strong performance features of your system, you can use them in all kinds of machine learning tasks, right? You're not limited to one thing. You can think about everything from regression to clustering and generative AI. So let me go through this in an example. So one of the first projects we did a while ago is on designing covalent drugs. So there is covalent drugs have been very wide used in the pharmaceutical industry. They're very potent, right? Because there's an electron transfer, and therefore they bind very strongly. But they're also they can be potentially quite toxic. So you want to really understand how they function and what their behavior is, depending on their structures. I guess there's not always, yeah, sorry. A covalent binding, that they have a covalent binding between so that there's that the protein binds to the drug and shares an electron. So this is one of the regions where which I guess that pharmaceuticals have not always have the full attention to, because they're sometimes hard to simulate. I mean, there have been aspirin, I think, is one of the first covalent drugs as well. But from a computational perspective, they can be quite challenging. So there's probably some under-discovered fields of covalent drugs that are still out there, if we would have better computational tools. So in this case, we picked certain molecules, these type of molecules there. So there was a data set that described the reactivity of these sets of molecules, and they have a certain warhead. So the thing on with the fluorides on top. So that's really the site where that binds to the protein. And so this is really the part that you want to have a full quantum mechanical description. So if you don't have a quantum mechanical description of this part, you probably, you're not able to calculate predictions of reactivity that make any sense. But at the same time, you want to incorporate the larger part of the molecule as well, because there can be some charge transfer that facilitates a binding. And so if you ignore the rest of the molecule, it might not be, you might not get the result you want. So you need to either simulate the whole thing in a quantum mechanical way, but that's way beyond the reach, of course, of any near-term hardware. Or you want to have these embedding strategies where you take the small part, treat it fully quantum mechanical, potentially on a quantum computer, and have the larger molecule in a different way. And then we extract these features. So this was the first part. So then we go to the first part here was selecting this molecule based on those criteria that it has some form of a locality. So one part that is very, deserves a very fully quantum mechanical description, and a larger part that we can treat with less accurate solvers. There is this data, and it's a use case that's important enough for clients. And so, of course, this is a sort of a toy case still, right? It's not a thing that that's actively in research, but it's interesting enough and relates enough to real world cases that it's interesting to consider. And so here is the embedding strategy that we then have. So in this case, it's relatively straightforward because it's very physically localized. So we see the fragment, which is the warhead, and the depth in the environment. But of course, this could be very different as well. Maybe you select certain orbitals that you treat as a fragment as well. Or of course, you can have so another piece of work, we did a very hierarchical model where we have not just a quantum mechanical solver with the quantum computer and a lower accurate quantum solver, but also molecular mechanics. So really having hierarchical models of different layers. So this can be as complex as you want. Then we have this fragment where we want to get some features out of. And so what we were looking at is how can we evolve this state in such a way and extract information that is useful. And so this is quite general, I guess. You can have any observable that you're interested in the initial state. Let me go through this quickly. So I just wanted to
ask a question. So you did time evolution on the previous slide.
Yeah.
I think why do you want to do that when you want to find, say, a drug binds to a protein? Are you time evolving it by moving it towards the drug, or what's that?
Yes. So I mean, so this is sort of how do you say it? Like a case where it's over exemplified. So there's a massive. We give the electron a kick and see what happens.
I see.
And so why time evolution? I think one reason is because I think that is one of the areas where there's most hope for a quantum advantage.
Yeah.
Second, because it gives a lot of information about the system, right? Particularly if you simulate the dynamics around a certain interesting spot, around bond critical points, around some phase transition, about some.
I see. So you're interested in dynamics, not in, say, how strongly it couples.
So I guess ultimately we're interested in any type of information that is predictive for that system. Doesn't really matter. Which is feasible on a computer to extract. Right? And so I guess time evolution often is one of those things that is maybe more promising. Yeah.
What do you use as your initial state? If there has to be a ground state or so, you still have to solve that.
Yeah, which is always the case, right? Yeah. So I guess here in this case we just use a Hartree-Fock basis state. Yeah. So bringing this together, there's a very simple demo or like overview that describes this thing. So the first phase is we select some molecules that we think are promising. Think about the fragmentation strategies where what can be the fragment that is our full quantum mechanical description. Select the active space, so select the orbitals that we want to take into consideration. Treat the rest of the molecule with a lower accuracy solver and extract some feature, which I think will show. And of course, this is already speed up many times. And so this feature can then be used for some next prediction.
So is this also a product that you're building and selling? This particular thing you showed?
CapGemini is not really a company that really makes a lot of money on licensing of projects. We typically a model that we also use, sort of accelerator, we call it, which is basically the idea that we just sell hours in the end, but we bring some IP, some product that will help the project, accelerate the project. So in this case, yes, we have a code base that we use that we are developing. We are working with a lot of different companies in this and also open source packages. So for example, Tangelo from Good Chemistry is one of the packages by SCF, but also other things. I mean, you also want to have your initial states. We did some work with Prometheum from QCware. Then later in the pipeline, there's more things like Q control for error mitigation. And so there's a whole range of things that we work with, some open source, some not open source, that we integrated into this framework. Yeah.
So the demo, the feature you just extracted, is it related to any chemical property you just used as a feature for machine learning afterwards?
So these features, so the observable that you measure can be, I guess it starts with some chemical intuition, right? Like if you maybe some bond critical point that you evolve around, but it doesn't necessarily have to be chemical intuition. You can also try to optimize that in a data-driven way. Yeah. Yeah.
Can you say, if you go to the previous slide, the graphs that you get out, what do they show? What is sort of the x and the y axis?
So I typically the y-axis is the time, relative time steps, and the x-axis is the energy.
The other way around.
The other way around. Sorry. Yeah.
So this is a very symmetric system. It seems to go back to.
Yeah, and I'm not 100% sure if this is. And I go through actual results. This is more of a demo. I'm not 100% sure if this is true data or if this is.
Oh, okay.
Just something
It's
someone
just an
draw.
example.
It looks cool.
But okay, so here there is real data. So this is the same graph as you see before, but then all these actual molecules. And so again, indeed, on the you have the warhead feature, which is typically some energy, but it could be any of the observable, right? Like one or two body density matrices or something else, and the time step on the other axis. And so the question is, is this useful? Are those features, can you use them for anything particular? And so what we saw here is we correlate these features to structures, is that all of these features have a certain peak at some energy, whereas other features have, and there's a slight difference here between this molecule 008 in the sense that it has an additional oxygen in its warhead, right? So that shows that at least there is some correlation between the feature that we obtain and the structure that we get, right? Even though maybe the warhead itself is the same, right? It's just an extra oxygen, so that already shows that there is some correlation between the features and the structures. So the question then is, what else can you start to predict something with this? So one thing was to predict reactivity. So here, these results show the reactivity predictions for various samples compared with truth data, which is DFT in this case, because there is no experimental data. But what it showed was that there is you can use this to predict it, right? So there's quite a good relationship between them.
Or at least you're making the same mistakes as DFT as well.
Yeah. That's a good point. Yeah.
I mean, the data in your machine learning model, like the training of the machine learning models, is also based on DFT. So is that right?
In this particular case, yeah. I mean, you can use it with experimental data, maybe. Yeah.
So it's good if it matches.
But this
Well, I hope so.
The machine learning works.
Yeah. Right. Yeah. And so in this case, I think there is some experimental data that validates these results. Right. It is still a relatively small toy problem.
Yeah, but I mean, by definition, right? Because you don't have a quantum computer to train this with yet. You're always within the bounds of
things we already know in some sense.
Well, yes, but also no, because I think this method is broader than the quantum computing. Right?
Oh, okay,
You
that's
could use
fair
your features in a purely classical way. And I think that the point so far is not necessarily showing the power of a quantum computer. It shows that the power of using quantum features, so features that describe quantum mechanical behavior in machine learning.
Oh, okay, fair enough.
And so one thing is what it shows is that these quantum features, which is, I guess, for many systems is very natural, right? That there is quantum features that are descriptive, that maybe right now we're not taking into account, but that are descriptive, and of course then the quantum computing argument comes in that if you would scale these features, they will become increasingly complex classically very quickly. Yeah. Very quickly, and that's how they're selected. Yeah.
Can you provide?
That's also what this next page is about. So if you would, so we know that these systems would scale very unfavorably classically, and so we want to see what happens if we increase the size. Does it make sense to increase them? So in one way, for example, to increase the simulation length, or to increase the active space. And in both cases, we see that the power of the quantum feature really increases, right? So and then there's of course a scaling argument that increasingly it will become beneficial to consider a quantum computer.
Can you provide?
2 slides, sorry.
Sorry.
Yeah, wait, so the quantum feature here, I should be able to see some quantum feature, and then
So the features are just these lines, right? Yeah.
but from that you conclude this difference based on like the presence of oxygen in 008 compared to the others.
So these features correspond to some of these molecules, and what we conclude here is that there is some correlation between the features and the structures, right? So all of these structures have a significant difference feature than the one with the different warheads.
But how do sorry, I don't see how is the orange line different to the others?
Yeah, it is maybe.
It's a little bit to the left, I think.
There is there's a different peak.
I think this is a fair point.
Here, can you remind us what the x-axis is here?
Time.
And the y-axis is undefined feature property.
Right, which is many. I'm not sure what it is in this case, but I think it was two-body density basis for some orbital, some energy.
If you have to time equals 0, you choose a very specific state that makes sure that they all sort of do something special after a certain amount of time.
Yeah, yeah.
Earlier you said you kick them, right? You have some time-dependent evolution.
Yeah.
You should give them a push.
Yeah, exactly.
Right, yeah.
There's a question online. Apparently the volume knob is turned down, so they can't speak up. But I promised to relay the question. The question is, what quantum features? What are the quantum features?
So the quantum features are energies over time of some observable of interest, and that really depends per case. I think in this case it was just reduced density matrices of some orbital. I don't know how exactly, but it was just energies over time. And in this case, like, so we give this electron a kick and see what happens. Okay, so the idea is so that if we increase the size of these features, then they become more descriptive, right? And so the next thing is how can we start to think? Oh, one more thing. So we saw about prediction with the linear regression, but you can do all kinds of modeling tasks, right? If you have something that is very descriptive for your system, you can think about all kinds of interesting machine learning, potentially generating new structures or based on these fingerprints, trying to find new molecules in this way, or clustering. Right, so in this case, we see that there is some we can cluster them and group these structures based on their victories. And I think there is one interesting example here that that we found was that there is one molecule, I think it's 161, so somewhere up there, it's hard to see. But there is one molecule that classically you might not categorize in the same kind of way. But because so initially you would think that it's a misfit there. But after consideration with the chemists that we worked with from GSK, we found that if you would not capture the quantum mechanics, you would categorize them differently. But in practice, they behave the same, right? So that's quite interesting that you get data here that you would not have gotten if you would not have taken the quantum mechanics into account. So this is one potential machine learning tasks. Next, more of a question like how does it start to? Oh, already talking too long. How does it start to work when we consider hardware? And of course, these circuits get very deep. How does this work on real hardware? Is approximate simulation also useful? And so what we experimented with is what if we experiment with different number of Trotter steps? What would that mean for the energies that we get? And so what we found was that that the only thing that we're interested in the end is there some is the feature that we obtain descriptive enough for a system? It doesn't have to be accurate per se. And so is there a strong dependency between the number of Trotter steps and the feature that we get? And so what we found was that there doesn't seem to be a very strong dependency between them. So even with very limited number of Trotter steps, we get still relatively good results. And so what we see here as well is different predictions of reactivity for increasing number of Trotter steps from 1 to 8. I'll speed up a little bit because I'm talking too long. So the next thing that we were thinking about is how can we further truncate the systems that we're looking at, given that there's so much inaccuracy already in the computers that we have. We might want to truncate our systems on sort of the algorithmic level much more, because that's not really where the bottleneck is. And of course, these systems that we have been looking at are very deep, right? So if you would just naively compile the systems, and even for 16 orbitals, we get for these systems gate depths that are like 100,000 or so, right? So very quickly becomes completely infeasible. And so only the very, very smallest number of orbitals are possible. So the question was, how can we sort of on an algorithmic level, before even considering hardware implementation, to truncate some parts of the Hamiltonian. And what we found was that many of these the coefficients of the Hamiltonian are very small in these systems, right? So they are not as descriptive as some of the bigger terms. So if we just truncate the Hamiltonian to just the biggest terms, we might still get pretty accurate results. And so what you see, that's what you see here, right? So the top scale is just the logarithmic scale, or the bottom one, where you see the size of the coefficients of the Hamiltonian. And so the question was, what if we truncate that, right? And what we see is that that there might still be pretty good results if you only keep the largest coefficients, because we're only looking at some parts of the system. We're not evolving it for indefinitely. We're only looking at the first X number of time steps. You might get good enough results for the features that we want. So what we see here is the on the top plot the percentage of features that we kept compared to the relative error, and so you can see that like it's very there's this trade-off. You can easily cut most of the pilot terms of your circuit and still get a pretty accurate result. You can go, I don't know, maybe to 10%, but then your algorithm would really lose from it. And so there's a bit of a trade-off that you can make, because of course the circuit depth decreases rapidly the more you cut. And so what we want to show here is that so in the top bar you see the level of truncation for a certain level, so from 13 to 25%, and all of them after X number of times that they become just noise basically, right? But up until the first time step, there may be pretty good accurate results still. And for the experiments that we are interested in, that's the only thing we care about anyway, right? So that is quite a powerful approximation method, I guess, because all the other things, I mean, we're not interested in anyway, and so we can throw them away. So then what we and to exemplify maybe that trade-off a bit more is that if you start really running this on real hardware, there is on the one hand you have your algorithmic approximation, so the number of terms that you keep in your Hamiltonian. On the other hand, and of course you want to make it as big as possible, the biggest possible circuits. On the other hand, you want to make your circuit as small as possible to run on real hardware, and you have to have some sort of a trade-off between the two to optimize your results. And so what we try to do is to see, you know, where is the trade-off? At what point does the hardware errors become more, how do you say that, like limiting than the algorithmic error? And so what you see here is at the top bar, there's where we got 14% of the terms of the Hamiltonian and evolved it for the first number of time steps. And at the bottom, 70%. So if you would have a perfect simulator, then of course the bottom one would be much more performant, but the circuit depth is that much bigger that it will well basically result to noise. And so this really is just a way to think about that. We don't only need to think about the hardware performance that we consider. We really need to map our sort of algorithmic level even before considering quantum hardware to match the same level of accuracy. So we try to push that a little bit further to see how we can go to 12 orbitals, starting with something like circuit depth of 30,000 or so, so really far beyond reach of any quantum computer. Got like 90% of the terms or so, and got into maybe something like 700 depth. So much more accessible, but still pretty far out of reach of any type of hardware. But I mean, it's still you know, a factor of 20 improvements. So it shows that, you know, maybe some of these circuits will be brought a little bit closer to potential than without these type of approximations. So to conclude, and then I wanted to show a few more examples of other types of work where we apply the same method. But of this truncation is that it's in the end, I mean, you have to deal with all these approximations that you have that you can take, and there's errors coming from many different places. It doesn't make sense if you have errors only coming if you have a very accurate system and then a very noisy hardware, right? So you have to balance the two. And I guess this is one way to do that, and particularly because in our case we're only interested in the first time steps anyway, right? So it doesn't really matter that it gets inaccurate over time because we're not using those data at all. So this was sort of trying to explain the method that we use and have developed. So really going from what are the systems that are interesting because they have some sort of interesting chemical pathways, where we can use some appropriate embedding technologies to use quantum computers at very small scales for features that we know would scale very favorably on a quantum computer and that we know are very predictive. But then there are, of course, many applications that we can think of. So one project that we did was for a consumer product company. It was Dutch, but no longer, and I cannot name it, but it's big. And they were interested in these esters. And so the question here is well, how can we predict these hydrolysis rates? So how can we understand the hydrolysis, how hydrogen swaps in and breaks this molecule apart as a pathway for biodegradability. So again, we have sort of this system that has these criteria, right? There's loads of data that we can use to simulate and predict hydrolysis rates. We have these systems that are that have a strong sort of localized quantum mechanical system that we want to treat with fully quantum mechanical. But we also want to have sort of a model of the wider system, and where we can then evolve some feature of our fragments that are used to predict, in this case, hydrolysis. Another project that we work on is on batteries. So batteries are also, I guess, quite interesting because just like drug discovery, this is this huge design space, right? There's loads of different things that you want to try out, different additives in electrolytes, different materials, different, under different conditions, different temperatures or whatever, different performance metrics like capacity versus recyclability rate or whatever. And they're also very complex chemically. So if you have these cathode materials like nickel or cobalt or something, they have these transition metals. So we know that they are difficult to simulate, and so it's potentially promising. And so particularly in this case, what we wanted to do is to see how can we have this sort of hierarchical model of embeddings where we look at the binding of the transition metal with the cathode surface, while taking into account if there's, for example, different additives in the electrolyte, right? So having these very different layers of accuracy and different solvers, and then in the end to predict certain reactions that contribute to degradation. One other project that we are currently working on is on carbon capture, and so I guess here's a sort of a similar story, right? Where there is again some very interesting quantum mechanical behavior. You really want to treat that with a fully quantum mechanical system, and there's also loads of data that you can use then to predict more macroscopic properties. So let me stop here. So there's the goal was in the end to have some sort of a framework that is also scalable, because there's so many different tools and we never really know what's gonna work out. So you really want to build something that is where you apply new techniques, and we have a whole range of things that we are looking at. So one thing, for example, is to see what if you have some sort of machine learning where you are, for example, only interested in the ranking of certain systems. You can take further approximations into the selection of your feature that would decrease the need for your hardware, the constraints on your hardware. So really trying to see the robustness of the whole pipeline, including the machine learning on the feature. There's many different embeddings and strategies that we're looking at. Maybe we can try to optimize the best way to fragment things, for example, by having looking at tensor networks and seeing where bond dimensions and how that could work. There's of course many different applications that this could apply to, and so this is just some examples of things that we are further exploring. I see that lunch has already of something came, so maybe let me stop there. Are there any questions?